This is a lecture on 11-2, tests using contingency tables. So these are chapter 11 tests, meaning all of the tests that are discussed in this section are all chi-square tests. The first test is called the test for independence. And if you recall contingency tables that are discussed in chapter 4, where you have columns and rows, what we're going to be doing in this section is constructing matrices. We are using a chi-square distribution. The chi-square test statistics has exactly the same formula as we did for the GOF test, where O is observed and E is expected. But instead of working with a column, what we're going to be doing is we're going to be working with a matrix. The expected value can be figured out by taking a row sum times a column sum divided by grand total. But the good thing is both T83 and T84 have the chi-squared test. That's the test for independence. That's the test that's going to be run in 11-2 for both of the examples that are presented in this book. What this book is doing is it actually spends about a page discussing on how to find these expected values of a matrix. In reality, that's going to be done in your calculator. So I'm going to skip over that. And I do want to outline the null and alternative hypothesis for this test. And the null and alternative hypothesis will always be the same for the duration of this section. It is a test for independence, so the null hypothesis says that there is no difference, meaning we didn't find any pattern. So it should say the rows and columns are independent of one another, and the opposite would be the rows or columns are dependent. So I'd like to actually underline these two words. The null hypothesis should say the word independent. The alternative hypothesis should say the word dependent. What I want to do is I want to jump into example. This is example 11-5 in the book. A researcher wishes to see if there is a relationship between a hospital and the number of patient infections. A random sample of 3 hospitals was selected, and the number of infections for a specific year has been reported. The data shown next. At alpha 0.05, can it be concluded that the number of infections, meaning columns, is related to the hospital where they occurred? So those are your rows. There's a couple of things that you might want to do before start with the contingency table. First of all, this is a contingency table. We study these in chapter 4. What we're doing right now is, instead of looking at probabilities within the contingency table, we're going to be looking for independence. So does the hospital is there a relationship between a hospital and the number of infections? In order for me to find the expected matrix by hand, I would need to first find all of these totals, because it's asking for the total of the columns and the total of the rows. Now the reason I'm doing that is to actually illustrate something. So if you add these up, you'll see that there was 246 surgical site infections, 136 pneumonic infections, and 200 bloodstream infections. And in the hospital A, we surveyed 119 people. In hospital B, we surveyed 79 people. In the hospital C, 384. Now, notice that a hospital B is obviously much smaller than the hospital C, and therefore this 3 for pneumonic infection might somehow be affected by that. This is why 11-2 presents two distinct hypothesis tests. One is called the test for independence, which observes the numbers in each category and finds if there's a relationship within numbers. And the other one actually talks about proportions, meaning percentiles, where it gets rid of this difference of the 79 versus 384 and gives a slightly different perspective on the same issue. And that test is called homogeneity of a proportion. So we'll first discuss this example, and probably on the next video I'll give you the other test, which is called the homogeneity of a proportion. So let's start here. Null hypothesis, alternative hypothesis. So what I want to say is somehow you want to include the word independent and something with respect of the number of infections and the fact that we're talking about hospitals. So a good way of putting this together is the number of infections is independent of the hospital. So you're telling me that, first of all, there's the word independent. I'd like to underline it. And the number of infections, that's your columns. The hospital, those are your rows. So there's an independence between columns and rows in this case. And the alternative hypothesis, you would rephrase exactly the same thing using the word dependent. So the number of infections there's an S right there. Infections depends on the hospital. So that's my null and alternative hypothesis. What we're going to be doing is we're going to be running a chi-square test. Remember, all of chi-square tests are one tail right. It's always on the right. Now, before we get into the actual test, what we need to do is we need to create a matrix within the calculator. And what we're going to do in this video is I'll finish this test writing down the decision of the hypothesis test, and on the next video I will show you how to do this in your TI-83 and TI-84 calculator. So if you run through all of the calculations, according to the book, the chi-square test statistic came out to be 30.698. you can then calculate the p-value, and in order to get the p-value, you actually need to know the degree of freedom. The degree of freedom is calculated by the number of columns minus 1. Let me include that somewhere in here. The degree of freedom is calculated by number of columns minus 1 times the number of rows minus 1. So in this case, I have 1, 2, 3 columns. Do not count the totals. So 1, 2, 3 columns in your matrix. So that's 3 minus 1. And I have 3 rows. So that's 3 minus 1. 2 times 2 will give you a degree of freedom of 4. So according to my chi-square CDF, the p-value came out to be 3.5 times 10 to the power of negative 6. So be careful to recognize those scientific notations. It does mean that this is a very, very small p-value. So alpha at 0.05 certainly is much larger than this p-value. So p-value is less than 0.05. If the p-value is less than alpha, we do reject the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis. So what we say is there's enough evidence to suggest that the number of infections depends on the hospital. Now, this test is very inconclusive, especially if you reject the null hypothesis, because why that there is a dependency, or what is the pattern of findings within the matrix is really unknown. If you go back, it could be as simple as this is just a much smaller hospital, therefore it has less infections. Or is there really an issue with the hospital that one hospital has more infections than the other? And that is observed or done by further research. So if you reject the null hypothesis, so if you do not reject the null hypothesis, that means that your research is done. There's no, everything's independent. We didn't find any anything, any correlation, any conditions or anything within the matrix. But if you reject the null hypothesis, like we did in this particular problem, that means that further research is necessary in order to find where the discrepancy is. As I said, on the next video, I will do this particular problem on a calculator, and then we'll continue on to the test for homogeneity over proportion.